Hi, in this video we will explain the DC analysis, how to do DC analysis in Cadence and what are the different options available for the DC analysis. And we will do a couple of examples also. We will do different type of examples to illustrate these options. Basically, DC analysis is used to find the voltage and current at a particular operating point. First of all, let's do a very simple example. Of a resistive divider. After that, we will move to other complicated examples. So this is my schematic window. And okay, I'm using simple resistor 1 kilo ohm. I put here. Then I want a voltage source of voltage, let's say 3 volt. Okay, and I need ground. Hide, place it here, press escape, just connect them together. And label the wires, just label them as in and out. The supply voltage I am labeling as in, and the voltage divider output I am labeling as out. Press X to save them. And see, here we applied a constant DC value. Here we applied a constant DC value of 3 volt. So it is not changing with respect to time or anything. That's a fixed value. And we want to, if we do the DC analysis, we can see how much current is flowing through these resistors and what is the voltage of the voltage divider. So it is also constant with respect to time, frequency and all. So in DC analysis you can see only the voltage and current at a particular operating point. So just go to ADE, Analog Design Environment, and here choose analysis. You can choose DC analysis and save DC operating point. So you should save this DC point for your analysis. It is enabled. Okay, and you run. So simulation is over. You cannot expect any graph in this because there is no graph actually. This is just a point, a particular voltage and a particular current. So nothing to plot here, but you will get the values. So you can see our voltage source was 3 volt. So resistors 1 kilo ohm. So total 2 kilo ohm. So 3 by 2 kilo ohm, the current we will get 1.5 milliampere through this branch. And the voltage across this resistor, it has shown here. The voltage across this resistor is 1.5 volt and the voltage across this resistor is also 1.5 volt. So voltage at this node is the voltage across this resistor and it is 1.5 volt as we expected. So there is nothing much in this example. I just started with this example, and we can go to little bit. You can go to example of a MOSFET. Okay, I'm deleting this. Delete. Insert. Now let's do the DC analysis for a MOSFET. UMC, I'm using UMC library. and here is the MOSFET. I'm using an NMOS here. Put some width 1 micro and I'm keeping length 0.5 micro. Okay, so placed it here. Source is connected to ground, body is also connected to ground, and for the MOSFET we need VGS and VDS. So I'm considering this as the VGS. I need VDS also. So this voltage is my VDS, so I am naming it as VDS. This name has nothing to do with simulation. I am just doing to recognize the voltage source by its name. Since my device is 180 nanometer, maximum voltage I can apply is 1.8 volt. So that is the VDC, and the VGS I can vary maximum of 1.8 volt, but it should be above VT for any good conduction. So I am using this as 1 volt DC voltage. I am using 1 volt. So okay, so this is the VGS. So if you want, you can name it as VGS. Okay, I am using different name, V underscore VGS. Okay, and save this. We can use the same environment, there is no problem. We choose the DC and we save the DC operating point so that we can check the result. Now run the simulation. Simulation is over. As usual, we cannot expect any graph in DC simulation. It is just an operating point. If we want, we can see the result. You can annotate the DC node voltages and those things. It's already did. So this node voltage, it is 1.8 volt, and so the VDC is VDS. That means V drain to source is 1.8. You can see that on the MOSFET also. And this is the node voltages. So what else we are interested? We are interested in the current and the other parameter of the MOSFET. For that, you can go to result, print, and DC operating point. We are very much interested in the DC operating point of the MOSFET. Select the MOSFET. Now you can see all the DC parameters of the MOSFET for this particular input, for this particular VGS and this particular VDS. So the current ID, all the parameters are here, beta effective and all the capacitance, and you can see ID is 78.21 microampere for this particular input voltage for this VGS. Suppose you changed the VGS to below VT, that means you used 0.2 volt. For this device, the VT is near to 400 millivolt, but now we used 200 millivolt only. So what we expect is we are not expecting a huge current here. Now we got a current of 78 microampere. The drain current is 78 microampere here, but if we decrease the VGS below VT, we should not get big current. So let's see that. Okay, here itself we can see the current through this source is just in picoampere. So the same current will flow through the MOSFET also. For your sanity check, you can go to print, DC operating point, and select the MOSFET. You can see the current ID ID is in picoampere only. That means the device is in cutoff. So you can check that region also. The region is 3. Region 3 means device is in sub-threshold. First, for the MOSFET, region 0 is cutoff. Region 1 is in linear. Region 2 is saturation, and region 3 is sub-threshold. So we give a 200 millivolt VGS. That means a system is not in cutoff but sub-threshold. That means VGS is not greater than VT. So if we use little bit higher value, suppose you use a 500 millivolt, and let's see how much the current is varying. So I didn't save. Okay, I saved and run the simulation. Now the current is 2.51 microampere. So result, print DC operating point. So you can see the ID is 2.5 microampere and the region is 2. That means it is in saturation. So clearly here VGS minus, what is the condition for saturation? The condition for saturation is VDS should be greater than VGS minus VT. Here the VDS is 1.8 volt, VGS is 500 millivolt, and VT will be near to 400 millivolt. So clearly the device is in saturation. So basically DC analysis, you can see in which region the device is working, what is the current through the branches, and all these. To find all these things, you can use the DC analysis. So in the DC analysis, you have some other options like you can change the temperature also. For example, with the same VGS 500 milli, VDS this much, I can change the temperature and see how the current is varying. So the MOSFET current through the MOSFET is dependent on the temperature. So you can go to setup and you can set the temperature. Now it is in room temperature. Suppose I increase the temperature to 100 degree. Okay. So before running, you see the current ID is 2.5 microampere. So in the room temperature. Now I changed the temperature to 100 and see the current is now 4.39. That means the current almost doubled its value when I changed the temperature. So this type of analysis you can do in Cadence, in DC analysis in Cadence. Another thing, you can do the DC sweep also. So till now I was doing, we were analyzing the device at a particular input voltage. If you want, we can change the input voltage and see how the current is varying with respect to input voltage. First of all, let's do that. Let us go to outputs to be plotted, select on the device. So I am selecting the drain current to be plotted. Okay. So M0 is my MOSFET and D is the drain. So I selected the drain current and go to the analysis DC. Here you have sweeping option. So whichever parameter you are selecting here to sweep, it will appear in the x-axis. For example, suppose I am using the component parameter and select component. After that, I selected the VGS. Okay, so after that select component, you click on this voltage source. So a window will pop up. Here you can select which component you want to change. I want to change the DC value. Okay. So again, go back to the analysis. So the component name V_VVGS. So I place the name VGS so that we can easily identify the device. Otherwise it will appear V1, V2 or something. So I want to start, I'm sweeping that value, so I want to start the VGS from 0 and I want to end the VGS at 1 volt, or you can say 1.2 or 1. Even you can go to 1.8 also, no issue. And the sweep type you can use automatic, then the cadence, it will select how many sweep points and what is the resolution, or you can give linear also. Step size also you can give. Step size you can give as 0.1, or the number of step also you can give. Total how many steps you can give. Okay, I'm using 10 steps. I'm pressing OK and run the sim. Okay, I forgot to mention one thing. So we are sweeping the VGS here. That means this VGS voltage will appear on the x-axis, and the drain voltage, the drain current we selected to plot, it will appear on the y-axis. So the graph we are going to get is the VGS in the x-axis and the ID, drain current, in the y-axis. So let's run the simulation and see. You can see the graph. So you can see the graph. The current, drain current, is in the y-axis. We sweep the parameter that VGS is a DC voltage. So this graph shows the variation of MOSFET drain current with respect to VGS. This is exactly what we expected. If the VGS is below VT, then there is no current. That means it is in cutoff. And the VGS is near to VT, it will be in sub threshold. So we can expect little bit of current. And if it is above VT, we can expect a lot of current. So this is exactly this graph is very familiar to us. You can see in every textbooks. Now instead of VGS, let's sweep the VDS. Okay, so VGS, I am selecting another component. Now I am selecting the VDS, and again I selected the DC. So now it is changed to VDS. So here also I am starting from there is no starting from 0 to 1.8, but this time I am using step size because I don't want this so many curve. I want only if it is 1.8. so okay, assume it's 0.4. okay, and now run the simulation. What I am expecting is VDS in the x-axis and ID in the y-axis. Okay, the graph is not very smooth because see, the graph is not very smooth. We can see that is because the number of points that we added is very less. So step size, instead of 0.4, if I use 0.1. okay, now you run the simulation again. See, now you got a little bit more good, comparatively good curve. If you want, you can make the curve better. So instead of step size, I am giving 1000 point. Okay, and run it. So now we will get a smooth curve. See? So this is the ID versus VDS curve of a MOSFET. And we can sweep not just the voltage, we can sweep any parameter. And now I am sweeping the temperature. Let's sweep the temperature. Temperature from I'm sweeping temperature from -40 to 125 degree. So the step size I want, okay, 10. I want the step size, so I'm putting 120. Let's see how it is. Current is varying with voltage. Temperature. So now I am expecting a graph with temperature in the x-axis and the current in the y-axis. So this is exactly what we are getting. It is the temperature in the x-axis and the current in the y-axis. If we want to get a very smooth curve, we have to add the number of points. Instead of step size, if I use a lot of points, then you will get the exact curve. Okay. Another example for DC analysis, another popular example is the transfer carrier of an inverter. So we have an NMOS here. I want to make it an inverter, so I need to add the PMOS also. So P, 2 micro width and 0.5 micro length I'm using. Yes. A drain, body is connected to VDD, is connected and it is connected. So this will be the output. I'm labeling V in, V out. So this is the V in, this is the V out. So the warning is this point is this is floating. So I want to plot the graph of V in versus V out. That is the transfer carrier of an inverter. So for this, I want to sweep V in and I want to see how V out is varying. So for that, I'm not interested in the current now, so I can delete it, and I want to plot the output to be plotted V out versus V in. This is what I want. So if you want both on the graph, you can select the both, and the graph, earlier we labeled it as VGS because we were using it for the MOSFET. Now we can make V in or V input or anything we can label. V input, okay. Save. And in the analysis, it is DC. And now we are going for a component parameter. Select the component. Now we need the input voltage we want to sweep. So select the input voltage. We want to change the DC value of the input voltage. Okay, so we want to start it from 0 to 1.8. Okay, and run the simulation. So this graph is very familiar to you. When this green is the green curve is the input voltage and the red curve is the output voltage. As you can see, this is the input node and this is the output node. So initially when the input is 0, the output is VDD. That means logical 1. That is a property of the inverter. If input is 0, output will be 1. 1 means logical 1. And when the input increases and finally it reaches VDD, that is 1.8 volt, VDD means logical 1, then the output is 0. So in between this, the output is going from VDD to 0. So this is the transfer curve of the inverter, and you can see it's in any textbook. So these are the uses for the DC analysis, and I'm stopping this tutorial here. Thank you for watching.